Streaming on YouTube also, because I don't use it. Oh, just saw you.
Are you using this computer?
Yes, yes. I have your presentation. This is your presentation?
Yes.
So I will introduce you. Yes. Okay, just a minute. Okay, for now, for the last talk of the day, we have Professor Wei Mao from the Xidian University, Hangzhou, China. And its talk on hardware-aware optimization of large language model for enhanced throughput on ARM CPUs. So the floor is yours.
Hello everyone, I'm Wei Mao from Xidian University, and it's my honor to give talk here. And this work also was presented in our 2025 AI class. And the title is Hardware Optimization of Large Language Model for Enhanced Throughput on ARM CPU. This is a brief outline. We will use model conversion, inference background operator optimization to co-optimize the large language model on CPU. Nowadays, the large language model have developed very fast, and natural language processing have undergoing a different paradigm and change. It's from a rule-based approach, statistical approach to machine learning and deep learning approach. And nowadays, the pre-trained large language model can demonstrate remarkable performance across a wide domain of natural language tasks. In this work, we're using Q1 model to optimize. And this model is developed by Alibaba Cloud, and it has multi-model extension and board applications, and also it performs very well on different datasets compared to the SOTA models. And in the right one is the blocks. It contains embedded layers, Q1 block layers, and several Q1 block layers, RMS normalization layers, and linear layers. The hardware platform we choose the Intel 710 CPU. It's based on ARM v9 powered structure. The reason we choose this structure because due to the fast development of IoT, and most edge devices are using ARM CPU. So in thus how to implementation large language models on the edge device, especially implementation on ARM CPU, is necessary to research. However, the large language models have tons of model parameters, and it also has large numbers of GMM and GMV operators in the prefib and the decoder phases. The corresponding hardware performance evolved slowly. It is challenging to deploy it in the wide applied size for inference. Also, in our work, we're using different technologies to improve the overall performance. First is the activation aware waiting optimization. method to reduce the memory usage and keep accuracy. Then we're focusing on the operator optimization and operator integrations to reduce the instruction interruptions. Besides, we also employ a Llama DCBP for fast implementation and pilot. This is the activation of the weight optimization method. By using this method, the significant weights are protected through activation of weight scaling. In this way, not all the weights are equally, not all weights are equally quantized, and only the redundancy weights are quantized to int it, and the 1% of most important, most significant weights are returned to floating 16 to improve the large language model accuracy. And according to the overall evaluation criteria, the best results are weighted and summed to calculate the performance test scores for each models by balanced memory usage, throughput for preview and diffuse phases, interference accuracy, and complicated with subsequent optimization method. A string we choose is int8 and the floating int solution. Besides, Lambda.cpp is using as the inference backend, and Lambda.cpp not only simplifies the setup but also delivers state-of-the-art performance of offering a range of optimization to cater to varying compatible hardware requirement and resource constraint. Besides for ARM-CPU, we also employ the SIMD instructors, which are mainly used for parallel computing. The following is the schematic diagram of the N-man array and the duty instructors, and it means the matrix multiplication and the signed dot product, which have significant optimization effect for the GMN and GMA and operator, which we mentioned before, because the GMN and GMV occupies large proportion of the whole operators. To improve the memory access efficiency and ensure the optimized performance of the GMN and the GMV accelerations, it is necessary to rearrange the data into contiguous memories to support SDT and MMARray operators. Before data rearrangement, the input needed to be repeatedly accessed to complete the computations for each channel. After rearrangement, the computation for each channel requires only a single access to the input, which largely reduces the intervention requirement. Besides, for the mask operators in inference, we have integrated the computation process. During computation, we directly set the upper triangle matrix to 0, eliminate the need for mask operator, and subsequent redundant computations in the attention block. The figures here shows the change of optimization rate with the sequence length. When the sequence length is greater than 100, the optimization rate remains stable at around 5%. Okay, in the final, let's conclude the optimization effects. After simple optimization, the prefill and the decoder phases exceeded above 5 times and 13 times speed up. And after using the operator fusion, the peripheral faces demonstrate 1.15 times speed up, showing the ratio peripheral and the ratio decode shows the best performance here after using the filtering and simmed operation. And showing our precision for the models, we choosing floating point city and instead of the original floating 32. However, due to the data rearrangement for simply preparing the data for the simple instruction, the additional space is necessary to ensure the data alignment. It also leads to an increase in memory usage when compared with optimized precision. Anyway, it's still good when compared with the original when compared with the floating 32 bit. And the final memory usage is reduced to about approximately half, while the accuracy have only decreased by less than 1%. Okay, that's all. Thank you. Any questions?
I have one question. In the case of the mixed quantization, how do you scale the processing? For instance, if you have a very large set of quantization, then for the scaling the processing it might be more complicated or it's not the case.
Do you mean how the AWQ work?
It's not in the
Do you mean this one?
Yeah, in the mixed quantization, then for the scheduling, how you have very diverse set of just choose a quantization site for one way and one quantization for another way, then it's more complicated to schedule it or not?
Yeah. If you use mixed propagation, the computation is a little complicated, but it reduces the load of the bandwidth.
Okay, so the total as a system is more beneficial.
You mean for the computation?
Yeah. We can discuss it offline.
Oh.
No other question? Okay, so thank you again. So this is the end of the workshop. We'll move to the visit of the lab. Thank you again for coming, and see you out of the amphitheater for the lab visit with François.
Yes, the lab visit will be short, 10 minutes, 15 minutes. We show you our design facilities. I hope you will appreciate that as we are from the same domain. So let's go there.
Who's the owner of this?
You can take your belongings, I think.
No,
Thanks.